want to try to do tonight is give everybody an understanding of how objects appear to move in the sky. If anybody's ever used a conventional telescope that moves in altitude and azimuth, which is just up, down, left, and right, when you're trying to follow an object, you'll notice that you can't just move the telescope in one direction to follow your object. Things seem to travel in arcs. So we're going to talk a little bit about that. I'm sorry, did you have a question?
No, I thought that you were asking who used that. So I just
so you use that type of telescope. Okay, yeah, very good, very good. So there's two different types of basic mounts that you'll see on a telescope. One is a alt-azimuth, which is short for altitude, which is up and down, and azimuth, which is left and right. And those are your conventional telescopes. There's also another type of mount called an equatorial mount. And those mounts move in arcs or circles to follow the arcs and circles that objects actually move in the sky. Very few objects are going to travel in a straight line across the sky. So we're going to talk a little bit about how those objects move and how we can locate them and find them in the sky, and hopefully by the end we'll understand. Yes, sir?
Would you like a demonstration piece?
I'm sorry?
Would you like a demonstration piece?
Sure.
I'll go get my dog.
Okay, yeah. Do you have setting circles on your dial?
No.
Okay.
Is it in pieces?
It's in two pieces.
I'll help you carry it in.
Great, yeah. So this, a Dobsonian is an example, most Dobsonians are an example of an out-as type mount, where the mounts move up, down, and left and right. I'm also going to show a program called Stellarium that any of you can download for free and put it on your computer, and I'm going to demonstrate the way, by fast-forwarding through time, kind of like they do in a planetarium, how these objects move, and I think it'll become very apparent to you. All right, so two of the really odd things that I mentioned earlier is called right ascension and declination. And right ascension and declination are the two coordinates that you can use to find any object in the sky. When you look at a chart and it lists an object's right ascension and declination, like for instance, let's say you wanted to locate the Andromeda galaxy, and you looked at its right ascension and declination coordinates, those coordinates are fixed. They never change. And unlike other types of coordinates, they will always remain constant. Polaris is very close to the true north and to the north celestial pole. So when you look down here at this picture of the Earth, you'll notice that there's a line drawn through the north and south pole, and those lines extend into space to the north celestial pole and the south celestial pole. So when we talk about the north celestial pole, we're just talking about extending those poles out into space. So when you look, you will find that the very end of the Little Dipper, or Ursa Minor, or the Little Bear, is a star called Polaris, and it's very, very, very close to that spot in the sky. When we're talking about right ascension and declination, unlike other things like altitude and azimuth, right ascension is written in hours, minutes, and seconds. And so when we say that something is at so many hours, minutes, and seconds in right ascension, that's what we're talking about. You can also think about things moving in the sky in a complete circle, and it takes 24 hours for them to move in a complete circle. As I mentioned earlier, altitude and azimuth, which is commonly abbreviated just to alt-az, like Eric's telescope over here, where it moves up and down and left and right. And I know that sounds a little bit basic. Moved in arcs and instead of up, down, left, and right. And they would be on either a wedge or something else where the motions are very different from this. And that'll become apparent here in just a second. Okay, so right ascension and declination, some silly jargon. The North Celestial Pole, or NCP, and the South Celestial Pole, or SCP, these are just the north and south poles extended into space, like I was talking about a moment ago. Now, the celestial equator is the Earth's equator, but at a much greater radius. If the Earth's equator was a rubber band, you could think of it as being elastic, then the celestial equator is the same rubber band just stretched away from the Earth. So if you can imagine a plane slicing through the Earth's equator and just extending into space. The horizon is something that obviously changes depending on your position on the Earth. So the stars that we will see here in North America may be very different from the stars that someone would see in Australia. I can't see from Dallas, Texas, I can't see the South Celestial Pole because the Earth is blocking my view. Conversely, they can't see the North Star. They can't see Polaris from down there because their horizon is different. So the horizon is very critical for what objects that you can see, and the time of night and the time of year that you're trying to observe objects. Zenith is going to be the point directly overhead, the point on the celestial sphere directly overhead. So when we say that an object is a zenith, you can think of it as being, exactly 90 degrees above from the horizon. The meridian is the line that extends from the north point on the horizon upwards through the zenith and then downward to the south point to the horizon. So what that means is if you were to face directly north and you were to draw a line straight up through the sky all the way directly to south, it's going to bisect the sky in half. And that line is called the meridian. If you're doing astrophotography, that matters because as your mount hits the meridian, it actually has to turn 180 degrees and then continue in that direction. It's called the meridian flip, and it is something to consider. There's also other considerations about the meridian when you're trying to align a computerized telescope. Okay, so I know this sounds a little bit confusing, but we're going to make it very simple. Right ascension is similar to the longitude on the Earth. The right ascension of an object on the celestial sphere is measured along the celestial equator. So think about longitude. Longitude lines run north and south on the Earth. So if you were to take and look at the sky and divide it up, right ascension is going to be those pie slices of the sky that line up with longitude. But unlike longitude, we're going to talk about those in terms of hours and minutes. So a complete arc, 360 degrees, is going to be divided up into 24 hours. Each hour, let's see, the unit of right ascension are hours, since the celestial equator is divided into 24 equal portions at 15 degrees per hour. So that means if you were to take out your protractor and you were to measure an hour out, that would actually translate into 15 degrees of angle. Any questions so far on that? Have I lost everybody? Okay, we'll keep going. Each hour of right ascension is divided into 60 equal minutes. Everybody knows that there are 60 minutes in an hour. For now, think of these units as measures of length or distance along the celestial equator, not time. So when we talk about an hour of right ascension, we don't mean looking at your watch for an hour. We're talking about 15 degrees. So in 15 degrees, we would have 60 equal minutes inside of that. By convention, the starting point, or 0 hours of right ascension, is a point on the celestial equator called the vernal or March equinox, where right ascension equals 0 degrees. There are 2 times a year that we have an equinox. One of them is called the March equinox, and the other one is called the autumnal equinox. And when you look at, everybody knows that the Earth is tilted. The axis of the Earth is tilted relative to the rest of the solar system. So as the globe revolves around the sun, it's going to be at a tilted axis like this. So if my fist were the sun, twice a year, this axis neither leans towards the sun nor away. It is exactly neutral twice a year, once during the autumn and once during the vernal equinox in March. When that happens, you will actually find that the terminator, that's the line, the shadow on the Earth that goes between the day and the night. At those equinoxes, that shadow is exactly 90 degrees perpendicular to the equator, but only during those 2 equinoxes. So during the March equinox, which I don't remember the exact date, but it's late in March, and I believe it's at high noon, right where that point starts is where 0 degrees, or actually I guess it would be 0 hours in right ascension is going to be. So depending on where you are on the Earth, your local right ascension time is going to be different. And we're going to talk about that in a little bit because it's not actually something that you need to calculate. It's something that you can figure out very easy. Okay, so does anybody have any questions so far about what right ascension is? We're going to clarify this a little bit better in a moment when I pull up my planetarium program and show you visually what we're talking about. Okay. So let's go ahead and move on, talk about declination. Declination is the other coordinate that you would need to locate an object in the sky. That declination is going to be similar to the latitude on the Earth. The declination of an object on the celestial sphere is measured northward or southward from the plane containing the equator. The declination of the equator is 0 degrees. The north celestial pole is plus 90 degrees, and the south celestial pole is negative 90 degrees. So did I really lose everybody? Okay. So we've got our declination, which has to do with which point along the 24-hour clock that we have. And then declination is going to be which of those circles that we're going to get on. And I'll show you exactly what that means. As it says here, the north celestial pole, which we talked about earlier, is very, very close to Polaris, which is at the very end of the Little Dipper. That's going to be plus 90 degrees. And if we could somehow magically see through the Earth to the other celestial south pole, that would be negative 90 degrees. Okay, so just remember that right ascension is the first coordinate that you need, and that's going to be in hours, minutes, and seconds. And declination is going to be in degrees. Okay, so here's a visual that will help to clarify this just a little bit better. If we notice here, 90 degrees is directly overhead. So this would be analogous to, your north pole. We call that the north celestial pole. And if you extended that up into space, you would see the tail of the Little Dipper. As we go down here, you see how we're going all the way down to the south celestial pole. And as we talked about earlier, this is going to be declination here. And this is plus 90 degrees straight overhead, and negative 90 degrees is going to be straight down. And notice how these look very much like our latitude lines on the Earth. And then here's the celestial equator right here. Now if we look at our right ascension time, you've noticed how we have 1 hour, 2 hour, 3 hour, 4 hour, wraps all the way around, comes around 23 hours, and then it resets at 0 hours. So notice that these lines are analogous to our longitude lines. It's almost like longitude that just extends straight out into space. This also right here shows you the vernal equinox, right at 0 hours. And this would be when, again, when the Earth is going to be tilted, and it's going to be a neutral tilt. The pole's neither going to be tilted towards or away. That's not really important to remember. And again, we're going to talk a little bit about how you will not have to worry about setting your right ascension time later. This diagram also shows something called the ecliptic. This is going to track or trace the general path of the sun, the moon, and the planets. And notice how they're at an angle to the Earth. And actually, I probably would have drawn this whole thing tilted and drawn the ecliptic straight and the Earth tilted, but we're not going to worry about that tonight. Okay, so does anybody have any questions about this diagram so far? Okay, we'll move on. All right, this is a screenshot of a planetarium program I'm about to show you called Stellarium. In order to locate an object in the sky, you have to know both its right ascension and its declination. We talked about that earlier. This is similar to finding a city on the Earth using latitude and longitude. For example, the location of Bloomington is 39.20 north latitude and 86.50 west latitude. So now we're going to go ahead and switch programs to Stellarium, and I'm going to try to make this a little bit less confusing to you. I think when you see it visually, it's going to make a lot more sense. This is a really neat program. I'd make a note of this and go home and download it because it is really neat. I've already configured. Are you guys looking for the class?
Yeah.
Yeah, come on in and have a seat. Have a seat.
Thank you. Good.
Welcome, welcome. So tonight we're talking about how to locate objects in the night sky. And we're talking about right ascension, declination, and also altitude and azimuth coordinates. So the first thing I'm going to show you is we're going to go ahead and move this over to where we're looking north. I think this will probably help you to understand best how to see the night sky. Can everybody see this okay? Okay. All right, so we're going to draw the constellation lines in here. And if you can follow my cursor, you see that I'm pointing to Polaris right there. This is Ursa Minor, or the Little Dipper. And that is the end of the asterism right there. If we go ahead and draw our equatorial grid, you're going to notice something that's really neat here. This point right here is the celestial North Pole. And if you were to measure that up from the ground, I think here in Dallas it's somewhere around
32.5 degrees.
32.5 to 33 degrees in North Texas, yes. I think in Carrollton I'm at 32.9. So, anyways, what I'm going to do is I'm going to run this guy and fast forward, and you're going to see that the whole sky rotates around that one point. That's not the only thing you're going to notice either. So we're going really fast here. And notice how the entire sky just continues to pivot around that one point. And it's always going to do that. So what that means is that as long as you have a clear view of the horizon, you will always be able to see Ursa Minor in Dallas year-round. All right, now the sun is rising.
Let me add something to that,
Yes, sir.
too. Just keep it going.
Okay.
Notice that, and Brad's already said this, right ascension and declination never change.
Nope.
Okay, they're a specific number. You can look them up in a book. All right, make sure it's a recent book because it does change over decades. All right, but you can look them up in a book, and what you have to do is pretend everything you see in the sky except for the planets are pinned up there with a stick pin.
That's right.
And just like cities on a map. Exactly the same thing. So if I told you, Dallas, Texas is about 96 degrees west and 32 degrees north, you could take out your cell phone and go to Dallas, couldn't you?
That's right. That's right. Like look at the
See, they never change position. They're locked in there. They're just moving around and around.
this is why the right ascension and declination coordinates of an object never change. See how it says 22 hours right here? It follows that star. It never moves off of that star. This circle right here is also 60 degrees declination. So if I wanted to find, like let's say I wanted to find that star right there, that's 1 hour right ascension, 60 degrees declination. Not exactly, it's a little bit off, but it's very, very close to that. So those coordinates never change. Now we're constantly rotating. We're always moving, but those coordinates relative to the sky, like Joe said, they're pinned down. Now the sun, the moon, and the stars, the planets are going to change a little bit every night. And so they will have a right ascension and declination coordinates, but they will change throughout the year and from night to night, just a little bit each night.
Is that because they're so close?
No, it has to, yes, because they're so close, that's right. That's right, it has to do with them being close and us changing our relative position to each other throughout the year and throughout, well, the year depending on which planet you're on.
And the ancient name for the word planet in Greek means wanderer. They wander around. They don't stay in the same place like the stars do.
Right.
So that's why they couldn't figure them out.
Yeah, like you said, even the stars change over decades, but they're the same thing, but they're so far away that the time is slowed down, right?
Right.
Yes, that's right. They will, over thousands of years, they will shift and they will change position, but during our lifetime, they will change very little. You can probably use the same star chart for the rest of your life for the kinds of telescopes that we would use as amateur astronomers. Now, people that are professional astronomers and people doing research, the stars change position a lot for them, but they're measuring in very, very minute precessions over decades. I've seen work that was done over 50, 60 years, and we would probably never be able to perceive of that. So everybody gets the idea of a couple of things here. Number one, the entire sky rotates around that one point called the celestial North Pole. Does everybody understand why that happens? Because that is the North Pole extended into space. It's just that the globe is constantly rotating around. So when you want to find an object, and you have what is called an equatorial mount, that equatorial mount will be angled where one of its axes is pointed directly at this celestial North Pole. And the other axis is going to turn like this and select these different concentric circles, which we would call declination. And on those telescopes, depending on what kind of telescope they are and how good the setting circles are, the right ascension hours and the declination degrees will actually be marked on the telescope. And you can rather than try to figure out and calculate your local right ascension time, what I would do is I would locate a bright star in the sky, and let's say, okay, Capella. And right here it says that it gives us the right ascension declination coordinates. Have a look at this. It says 5 hours, 16 minutes, 41 seconds. Now your setting circle dial on your telescope is probably not going to go that far. Now, but some of them have digital setting circles that are incredibly accurate. And so if you have what's called digital setting circles, it means that your telescope has what's called an encoder on it, and it knows exactly where it's pointed. And so it would tell you, okay, well, I'm at 5 hours, 16 minutes, and 41 seconds, right ascension, and my declination is 49 degrees, 59 seconds. I'm sorry, 59 minutes and 51 seconds. There are 60 minutes in a degree, and there are 60 seconds in an hour. I'm sorry, 60 minutes in an hour and 60 seconds in a minute. So whenever somebody says that something is at 45 degrees, 59 minutes, there are 60 minutes in a degree. So depending on the resolution of your setting circles, you may be able to get very accurate with this, or you may not. But at any rate, what I would do is I would locate Capella manually. It's a very, very bright star. You can see right here tonight, well, actually, this is not tonight. This is the 5th, because we kept fast forwarding. Jupiter's going to be very close. It'll be extremely bright in the night sky, and we'll look over and see Capella. Dial in Capella visually, manually with your telescope. Once it's centered in the eyepiece, you'll rotate the right ascension dial on your telescope to be, 5 hours and 16 minutes, if it's got that degree of resolution on it. And once you've got that dialed in, I'm talking fully manually. There's no computer involved here. Remember, the right ascension and declination coordinates of an object never change. Or, I'm sorry, of an object like stars and things that are not planets, not the moon, and not the sun. Once you get that, then you could say, okay, well, I would like to find the coordinates of, let's see, what might be up right now, M34, let's say. And if I were to go to look at a star chart, paper star chart, and say, what are the right ascension and declination coordinates in M34, it would tell me that they were 2 hours and 42 minutes, right ascension, 42 degrees, 47 minutes, declination. I would look at the dials on my telescope, and I would move my telescope to those readings on the dials, and your telescope is going to be pointed either at that object or very close to it. So that's the way that you would use right ascension and declination setting circles on a telescope to locate an object. So does everybody understand why a given object's right ascension and declination coordinates, excluding the planets, why their coordinates never change? For the same reason that the coordinates of Dallas, Texas will never change, not in our lifetime anyways. Okay, now we're going to move along to something a little bit different I'd like to show you. And this is going to be altitude and azimuth. Now you'll notice that this altitude and azimuth grid looks quite a bit different than the equatorial grid. The equatorial grid, everything converges right there at the celestial North Pole. That is not the case with the altitude and azimuth grid. Altitude and azimuth is strictly degrees. Altitude is how many degrees above the horizon. That's going to be 45 degrees, and that's going to be 90 at zenith, right overhead. So it's quite a bit different the way that these work. And I also wanted you to see how this actually plays out when we fast forward through the time here. So notice that the sky is moving, but the coordinates are not. So what does that tell you?
It's fixed relative to your position.
It is fixed relative to your position, but what it also means is that from one moment to the next, the altitude and azimuth coordinates of a celestial object is constantly changing. So a lot of telescopes will have setting circles on them that will tell you how many degrees in azimuth, north, south, east, or west I'm pointed. If it says 90 degrees, that means I'm pointed dead east. And if it says 45 degrees up, then I'm pointed 45 degrees above the horizon. But if that's changing from moment to moment, how do I know where a given object is going to be using altitude and azimuth coordinates?
Based on time?
I'm sorry?
Based on time?
Yes, it'd be based on time. You'd have to have a computer. You're going to have something that's going to calculate those coordinates for you. So you're going to need a laptop. You're going to need, you might have to have a program that's going to tell you the altitude and azimuth coordinates in the future so that you would know at exactly 7:53 p.m. tonight, Jupiter is going to be at so many degrees azimuth and so many degrees altitude. And that's going to change every moment of the night. So altitude and azimuth coordinates are in some ways less convenient because they're constantly changing and you don't know just intuitively where they're going to be. It changes radically depending on your position on the Earth, time of day, time of night, that sort of thing. So again, as we cycle through this, if you'll notice, before, the equatorial grid moved with the sky. The azimuth grid does not move with the sky, and the coordinates of a given object is constantly, the altitude and azimuth is constantly changing. So if you've got a device, let's say you have a cell phone or a palm-top computer or something else that can give you the moment-by-moment coordinates, it'll work. I mean, you can then use that to locate the object with using the setting circles of your alt-az mount. The advantage of this is that you don't have to do an alignment like you would with an equatorial mount. With an equatorial mount, you have to make sure that that is pointed directly at the north celestial pole. And if you'll notice, there is actually no star exactly at the north celestial pole. Polaris is very close, and probably for visual observation, Polaris is fine. But what if you set up during the day and you can't see the celestial North Pole? What if you can't see Polaris? Well, now you got to guess. And so for that reason, equatorial mounts are sometimes harder to set up, and that's why a lot of times you'll hear people recommend that a new amateur astronomer not use an equatorial mount because of the complexity in setting it up. But if you do have an equatorial mount or an equatorial wedge or something like that, it makes it very, very convenient to use for locating objects. Okay. So does anybody have any questions so far? Have I confused everybody to death? Yes.
Yeah, so thanks for asking. This Dobsonian telescope, so we are, me and my wife, we are beginners.
Yeah.
And we got a Dobsonian telescope, and like we bought a new one.
Okay.
The thing is, you mentioned setting circle. And it is, and this one, like obviously moves on the altitude and the azimuth.
That's right.
Way, right? Not the equatorial way.
That's right.
But can I buy a setting circle separately? I mean, it doesn't come with it.
Absolutely. In fact, that's a perfect segue. We're just about to talk to that in the next slide. So let me get through this slide. When we get to the next slide after that, we'll talk exactly about those. And in fact, if you have everybody pretty much has a smartphone now. So if you like to carry a smartphone around with you, we can rig your Dobsonian up with some very basic setting circles. And we're going to talk about a little device here that I picked up at the hardware store that will make your telescope and your cell phone basically a computerized push tube. It's very nice. I've used them before, and they're really fun to have. So let me go ahead and get through this slide and kind of reiterate some of these points that we just talked about, and then we'll talk about those setting circles for your Dob, and they're very useful to have. All right, so practical uses for right ascension and declination, and alt-az setting circles. They can be used with accurate setting circles to find objects in the sky. We're talking about right ascension and declination, or altitude and azimuth. However, most telescopes do not have very accurate setting circles. I have 2 equatorial mounts at home, and they have right ascension and declination manual setting circles on them. I don't know that I could find anything with them. They're so tiny and the resolution is so small. Does everybody know what I mean by resolution of a dial? If you were to look at, I'll tell you what resolution is. If you were to look at a yardstick that only had the inches marked on it, that would be very low resolution. If it had the half inches, that would be a little bit higher resolution. But if it went down to a 32nd or a 64th of an inch, that would be extremely high resolution of a measuring device. So on an altitude and azimuth or on a right ascension and declination, when we talk about the resolution of a dial, it means how far does it break it down? Does it go down to hours? Does it go down to minutes? Does it go to seconds? And you think about how big the dial would have to be to have that high of a resolution. So it's rare for you to find scopes that have extremely accurate setting circles. A lot of times people will set up what's called a Schmidt-Cassegrain telescope on a wedge, and a lot of those will have very, very large setting circles. And just because of the real estate of those setting circles, there's the space to put those small divisions on there and make the resolution of those dials very high. And I've seen people with Schmidt-Cassegrains on an equatorial wedge, and they're very, very useful. Hugh has a couple of them that are very useful. Okay, so if you have a planetarium program like what we just used, they're very, very handy for locating the right ascension and declination, or especially the out-as of an object. Does everybody remember why we probably will need a computer program to tell us the out-as coordinates? Because they change constantly. That's right, that's right. Okay. Also, if you've got a computerized telescope, one that automatically finds objects for you, what we call go-to telescopes, and then tracks them in the sky, or even if you have a digital push-to telescope, the meridian is used to align certain mounts on two stars, each one on opposite sides of the meridian, and to image objects across the meridian. That's like the flip that we talked about earlier. So what we're talking about is if you have a go-to telescope and you want to do a two-star alignment, it's best if you do them on either side of the meridian. If we were to pretend that this line right here is running north and south across the sky, we would want to pick one star from the east and one star from the west and do our alignment with that, either with our go-to or our push-to telescopes. The meridian flip is something that would happen while you're doing imaging on an equatorial mount, and unless you're doing that, there's no reason to worry about that right now. Okay, so as he just asked about altitude and azimuth setting circles on a Dob, this is a very excellent example of altitude and azimuth setting circles on a Dob. This picture right here, and if you'll notice, you've got a 90-degree angle dial right here, and you've got a small pointer that is likely adjustable so that you can make minor adjustments to it. This particular type of dial is going to require that your base be very, very level. So you're going to have to find a very nice place to put it, or you're going to have feet that you can adjust to level this. And I'll show you how we can get past this in just a minute. This is not my favorite way to do this. There are better ways. However, with the azimuth dial, this is what points you so many degrees north, south, east, or west. You'll notice that somebody has printed out and laminated this huge dial that goes in 360 degrees, and there's a little pointer right here on that dial. So what you do is you set that pointer on 0 degrees, and you pick up your Dob and you face it north and set it down. You look through the eyepiece, and you locate Polaris, which means that your telescope is pointed almost perfectly north. And most of the time, like on my Dob that I've got a small Dob at home, and this is actually on a magnet that allows it to slide back and forth. So I have some minor adjustments that I can do to make sure that that needle is just dead on 0 degrees. So I pull out my cell phone or my planetarium program, and it will tell me that a given object is at 32 degrees azimuth. So I point this thing until it goes to 32 degrees altitude. And then it says, okay, 52 degrees azimuth. And I'll rotate the telescope left and right until my little needle down here is pointing at 52 degrees. And if I have a wide-angled eyepiece with low power magnification, then I'm probably going to be able to see the object in my eyepiece, assuming it's not, little bitty faint object. And so what you have here is what we would call a poor man's push-to. And that does not mean that you're poor. It just means that you've set up a very convenient way to find things. Now, what I believe we have on the next slide here, here's a really good example of somebody who has made a really customized, beautiful azimuth setting circle. What they've done is they've cut this area out of the top part that rotates, and they've set their setting circles on the base that does not rotate, and then they have their pointer here, and it's very likely that this pointer is adjustable a few degrees either way, so that you can true it up with where it actually is. And that's actually a very pretty one. That's very, very nice. The other thing here is an object called an inclinometer. I bought this one at Harbor Freight for 20 or 30 bucks. And what it's designed for is when you're using a saw and you want to put a custom angle on a board that you're cutting or any surface that you're cutting, this will tell you exactly the angle that your blade is at, and it's got some really handy magnets on the bottom of it. Well, as it just so happens, I bet yours is not metal, is it?
Yes, it is.
Oh, it is, okay. So this just happens to fit perfectly on your daub, and it will tell you, and your daub doesn't even need to be that perfectly level, because it doesn't matter. Even if it's off a little bit, this is still going to tell you how many degrees above the horizon your telescope is pointed. So right here, I have my altitude, digital altitude. In fact, this thing has a resolution of down to 100th of a degree. Now, it's probably not going to be that perfect because the optical axis is not going to be perfectly aligned, or the mirrors are probably not perfectly aligned with the optical tube, but it's going to be darn close. And so when you combine one of these, like that, and I look on my little program on my phone and tells me, okay, M34 is at 72 degrees altitude. I move this until that little guy says 72, and I say, okay, that's great. And then it tells me, okay, well, we're going to be at 52 degrees azimuth, so I'm going to rotate until my dial down here says 52 degrees azimuth. And when I come over and I look in my eyepiece, I might have to move it around just a tiny little bit. Oh, there's M34, okay. And you're done. And so it's very convenient, and you didn't spend hundreds of dollars more on your telescope, and it's very, very nice to have. But they also make manual inclinometers. They have it's almost like a plumb line that just hangs down, and then there will be an angle. You know, it tells you the degrees, almost like a protractor. And as you move it up and down, that plumb line will change. But the resolution's not nearly as high as one of these. And so these are extremely nice to have, and if you can find one. I don't find these in very many places. In fact, the only place I've ever seen them for sale has been either online or at Harbor Freight. They don't seem to sell them at Lowe's and places like that. Yes, sir?
I'm sorry, what was the name again of this thing?
It's called an inclinometer or a digital angle gauge. Like an inclinometer. Inclinometer.
See that one on the screen there, that Wixie?
The Wixie? Yeah.
You can look that up on Amazon and buy it.
Yeah.
You can buy that right off Amazon.
Okay. That's the best way to do it. Now, you will notice, though, that it's not backlit, and I don't think any of them are, because none of them are designed to be used in the dark. So you may want to... I saw there's a guy named Brad who custom built a beautiful daub, and he likes to use things like this, and he goes to Fry's, and for about $1 or $2, he buys these little bitty LED lights that have a clip on them, and he paints the lens red, and the light is always, a little red light is always shining on that thing. And it's actually cheaper to buy those. If the batteries run out, throw them away and buy new ones, because the batteries cost more than the lights do. But it's a really, really fun way. I rigged up this exact setup on my 8-inch Dobsonian, and the very first time I tried to locate M13, which is a giant globular cluster in Hercules, it was right at the edge of the eyepiece when I pointed at it. So it was very, very, very close. What I did was, to make it more accurate, is I pointed it directly at M13. Again, I looked on my phone at the program I was using telling me where M13 was. I adjusted my azimuth setting circle just a little to be pointed right at it. And you can also put little shims under this and slightly move this thing up and down. Or you could say, well, I know it's half a degree off. And so you always just know that I need to point either half a degree high or half a degree low. But it really helps, especially when you're starting out. I don't really use these anymore, though, because now I do something called star hopping, where I manually find objects, and it's a little bit more challenging. But this is a wonderful way to start without a huge investment. Fully manual daubs are really, really wonderful instruments. You can get very nice, bright, clear views through them, and you don't have to spend a ton of money, and they don't require any batteries or power. So they're a wonderful thing to have. Okay, does anybody have any? Yes?
The azimuth circle?
Uh-huh.
Is there any such other advice that you have to have that one installed, or do we need to do it ourselves? I mean,
Let me give you one if you want to buy it. Okay, it's kind of pricey.
Yeah.
There's only one manufacturer I know that has a manual setting circle that you can buy and install on any Dob. And that is Apertura.
Apertura.
Apertura. Apertura telescopes. If you'll go to his site and look around a little bit, he sells it appears to be metal. And basically the Dob sets on it. All right, it's like $120. The Dob sets on it, and that's your azimuth. And then he sells this very thing to go along with it.
Yeah.
Yeah, but you can buy that
I mean,
off
if I
Amazon.
pointed to dead north, I could myself draw it. I mean,
Yeah, well, yes. If back up one slide there, or two slides.
Where do we talk about? Yeah.
Yeah, right there.
CloudyNights.com. That's actually where I downloaded mine from. I downloaded the setting circle, went to FedEx Kinko's, printed it off, had it laminated, and all I had to do was take the rocker panel off of the base, set my setting circle down, and then reattach the base. Obviously, I had to poke holes through the laminated paper, but it was very easy to do. I
but
mean,
once you do that, you still have to align 0 to north.
yes, you do. Yes, you do. So what you would do is you would go ahead and hopefully you've got this little pointer here where you can slide it a little bit left and right. But you go ahead and put it on 0 degrees. And then you say, okay, well, that looks pretty close to north. So I'm going to take my telescope and I'm going to, well, let's see, the first thing I did is I set, let's say it's setting off over here, and I've got it on 0 degrees. Well, now I'm going to have to pick up my telescope without rotating that dial and try to get it as close as I can to 0 degrees. All right, so I'm generally pointed north. My pointer says it's on 0 degrees. Now I'm going to look through the eyepiece, and I'm going to get Polaris in there. And I'm going to notice that my pointer is just a little bit off of 0 degrees. Hopefully my pointer is such that I can slide it a little bit. I'm going to bend down, and I'm going to move my pointer until it's right at 0 degrees. And at that point, you're golden. At that point, you know that you are pointed at true north. And let's say you go to your first object, and it tells you that it's going to be 83 degrees, almost right east. So you're going to be pointed about 83 degrees. And it's just a little bit off, let's say. Okay, fine. So I locate the object. It says it's at 83 degrees, but I'm really at 85. So I'm going to go ahead and put it in there, and then I'm going to adjust it again. You may find that through the night it may get bumped or it may be a little bit off, but it's going to be fairly close and at least give you an idea generally where the object is in the sky, and so that you're not completely lost. And then you stick your inclinometer there on the top, and that's a no-brainer. The other nice thing about the inclinometer is that if you set it at the very, very end of your optical tube, you can use it a little bit as a counterbalance weight. You know, especially if you get some of those heavier eyepieces on there, or if your telescope's a little bit unbalanced, this can help. So, but yeah, check out CloudyNights.com and look at the equipment in the equipment topic, and it should be pinned to the top of the page. And one thing that they have, the setting circles, they have different ones for different size Dobs, but those are just general guidelines. You may have to, I think they're all PDF, I think they're Adobe PDF files. So you may have to expand, like print them a little bit bigger or a little bit smaller. I wound up having to shrink mine by a little bit so that it would fit on there. But it doesn't have to be absolutely perfect, and I would err on the side of it being slightly smaller. Like if you notice this one, it looks like it's recessed from the edge just a little bit, and that's the way mine is. And that's fine. It would be better for it to be recessed a little bit than to be hanging over the edge. So you may want to try to print it first before you laminate it and see if it fits before you pay to have it laminated. I've also found out that if you cut it out first and make it physically smaller, that it's cheaper to laminate because they charge by the inch. Yeah, that's right. So there's little tricks that you can do. Of course, if you've got a buddy with a laminator, that's the best trick. Okay, so does anybody have any questions about the setting circles, right ascension, declination, altitude, azimuth? Is everybody okay with that? All right. Let's see what we've got here. Okay. So now I'm going to talk about one of the most wonderful inventions that's ever come to amateur astronomers other than a telescope. It's something called a Telrad finder. Once I got one of these, I never ever wanted to use anything else. There's nothing wrong with other finders. Eric has a finder here on his dock that is it's a small refractor telescope that has crosshairs in it like you would find in a rifle scope. So if you wanted to point your telescope, let's say at Jupiter, you would look through the finder and you would put Jupiter on the crosshairs. This has got very low magnification compared to the big telescope. I can see much more of the sky with this finder scope than I could see through the telescope. So if I was only looking through the telescope to locate an object, it would be very difficult. I might be within a degree of that object and never see it moving around. But I'll look through the finder scope and boom, there it is. Now, what Eric did is he started with his finder scope being aligned with his optical tube. So I don't know what he does, but what I do is out during the day, I pick an object that's as far away as I can possibly see. I like the tops of water towers that are at least a mile away. And I'll make sure that I can find the water tower in my main optical tube in the very, very top point. Then I'll look through the finder scope and I'll adjust the screws on it until the crosshairs are also pointed at the very top of that water tower, and I know that they're both aligned. One of the biggest complaints that I hear from people that are starting out in amateur astronomy is that they can't find anything through their telescope, even with their finder. Well, it's because they're not aligned. Well, the same, of course, is true with the TELRAD, but TELRADs are very different from those kind of finders in that they have absolutely no magnification whatsoever. The way that you look through a TELRAD is you look from the back straight through here. All this is right here that you can't see from this view. I should have brought mine in. I've got one in the car. When we do our outdoor session here in a few minutes, I'll show you my TELRAD finder. And everybody make sure that you come and look at my TELRAD because it's, I think they're about $30 right now. And just buy one. It's the best thing. So what there is there is an image that's projected up here on this clear glass or plexiglass pane. And when you look through it, this is what you're going to see. You're going to see a bunch of red concentric circles. And those are not just randomly chosen sizes. These are very, very specific sizes. The outer ring is 4 degrees. The inner ring is 2 degrees, and that little tiny one in the middle is half a degree. So if I know that a faint object is 4 degrees away from the star called Deneb, I know that if I put the star Deneb over here, then my object is going to be probably right over here or somewhere along this line. So this helps you to measure the sky in degrees. It's very, very, very useful for that. One of the things, I don't know if it's on the next slide or not. Yes, it is. Okay, so TELRAD circles on a star chart. Do you see a similarity between the circles on the TELRAD and the star chart? Well, that was done deliberately. These TELRAD circles can show you, like for instance, this is extremely useful, and it's very lucky that it lines up this way. This is the constellation of Taurus right here, and right in here we have the Hyades, which is a huge, huge open cluster that makes the horns for Taurus right here. As the horns extend out, you can see that about 2 degrees away from this bright star right here is M1, the Crab Nebula. It's a planetary nebula. It's what's left of a dying star. And with a TELRAD, all you have to do is look through the TELRAD and put that bright star right here on the edge of this 2 degree circle, and M1 is going to be approximately in that hole right there. So you just look through the TELRAD, you put it, you can even see it's actually not on the circle, it's just a little bit outside of that circle. And also if you drew a line between here and there, you would notice that M1 is not on that line. It's inside just a little bit. And it's extremely useful for finding all kinds of things. So we can measure those distances in the sky using the TELRAD. What I've done is I have the Sky Telescope Pocket Atlas, $13 off Amazon, and it's something that I use constantly. In the front of this, I don't know if you can see this or not, but it actually has the TELRAD finder drawn to scale for the star charts. So what I did is I made a copy of this page with a TELRAD circle on it so that I can have a clear, transparent TELRAD circle. I don't know if you can see that, it's very, very tiny, drawn to scale. So as I'm looking through my star chart, I just take my TELRAD circle here and I put it on the star and I say, okay, well, that object is so many of those circles away. Sometimes I have to use 2 TELRAD circles. But since it's drawn to scale, what I'm going to get looking at my star chart is going to be very, very, very close to what I'm actually going to see in the sky. Does everybody understand what I'm talking about? So instead of trying to use altitude and azimuth coordinates, now I'm using, a star chart just like they have here and these Telluride circles. Now you can download star charts that already have the Telluride circles for free. You can put them inside of plastic binders. Anybody know why we want them inside plastic instead of just out loose? The rain and the dew. At night, you'll find, I never realized how dewy it got at night until I started doing astronomy, and I didn't even think that even Carrollton that it got that dewy at night. But if I leave paper out at night when I'm doing astronomy, it'll be soaked and it'll begin to fall apart. By the way, this is pretty robust. It's not laminated, but I've taken this thing outside a million times and it's been fine. But if you print something off on your home printer, you need to put it inside a plastic sleeve so that it's not going to get soggy.
Just don't leave the book out for days.
Yes.
It doesn't do any good.
Yes, I left the last one out for, actually it was probably a couple months. And when I
Really?
came
Oh,
back,
wow.
well maybe it was a month, I don't know, it was a while.
It was a while.
It got rained on multiple times and it eventually will die on you. So now you can also photocopy these pages, put them inside of plastic sleeves and leave this one inside in pristine condition. And it's really neat. The other thing that's cool about this first page in this chart right here is that it also lists a measuring tape for angular distance, and it also has the star magnitudes drawn, where the brightest magnitude is a huge circle, the medium magnitudes are smaller circle, and the little magnitudes are very, very, very faint. So as I look through the star chart, I can look at a certain star like Castor or Pollux, and I can slide it up and down and say, okay, well that's somewhere between a mag 1 or mag 2. So I know when I look up in the sky, that's going to be extremely bright. Magnitudes are counterintuitive. The higher the number, the dimmer it gets. So a mag 10 star is going to be very dim compared to a mag 1 star. So if I'm looking in my star chart here, even though it may show me this tiny little star here, I look and say, oh, wow, well, that's a mag 6 star. I'm in light pollution and the moon's out. There's no way you're going to see that star. So it kind of gives you an idea of whether or not you might be able to see the star given your seeing conditions for the given night.
So does what stars you are going to see, does it depend on your telescope also? Whether it's an 8-inch or a 6-inch?
Yes, yes. Typically, everything else held equal. The bigger aperture the telescope that you have, the fainter the objects that you are going to see. That's not always true, but I would say most of the time that is true. So if you have a 6-inch Dobsonian, and you had, let's say, a 10-inch Dobsonian or a 12-inch Dobsonian, you're going to be able to probably see fainter stars with the 12-inch Dobsonian, especially if you were both at the same magnification. So let's say your 6-inch telescope, you're using a combination of eyepieces where you're right at 200 times magnification. And we jump over to our 12-inch Dob, we put the right combination of eyepieces on there where we have 200 power. Looking through the same telescope, the 12-inch Dob is going to be brighter than the 6-inch Dob at a given magnification.
And in Dallas, light pollution, what kind of magnification can I expect to see?
Well,
6, 4,
Oh, you mean magnitude? Right.
Looking magnitude on location,
It depends.
it depends, it varies.
There are several resources that you can do online that will help you to determine your local seeing conditions. They're going to vary from night to night. It's going to depend on cloud cover. It's going to depend on light pollution. It's going to depend on turbulence in the upper atmosphere. It's going to depend on whether the moon is out or not. There's nights where I have gone outside and looked up and it looked to be like a gorgeous night. But when I look through the eyepiece at certain objects, they're just waving because of turbulence in the upper atmosphere. We call that seeing. So go and Google clear sky chart, and you will find one relatively close to you that will show you a forecast of what your seeing conditions are going to be for that evening. The other thing that you can do is Google light pollution maps and try to determine the level of light pollution that you have in your area. A lot of folks, especially in the urban and suburban areas, have done a lot of work to catalog the levels of light pollution, and I think it's done very well. And it will give you different zones and tell you what your limiting magnitude will be. So let's say that you're limiting magnitude. Remember, magnitude works backwards than you would think. A magnitude 10 object is much dimmer than a magnitude 1 object. So let's say that your limiting magnitude is 8. So you can't see anything fainter than a magnitude 8. And you want to look at a galaxy or an object that says that it's a magnitude 10. Well, you're probably not going to be able to see it. Now, one of the things I brought with me tonight that's in the car, and then we'll pull it out, is a light pollution filter. Light pollution filters do not perform magic, but they do help a lot within certain boundaries, and you also have to gauge your expectations. All filters, every filter that you're going to buy is going to reduce the amount of available light that comes through your telescope, and there's no way around that. All filters are going to reduce it. It's kind of like a lot of things. You have to balance out the benefits with the consequences and see, does it work? I have found that for Carrollton, Texas, my Celestron light pollution filter works magic. What it does is it makes